Welcome back to the channel. In today's lesson, we'll see the Laplace transform of differential equation. We'll be looking at the Laplace transform of the first order differential equation. It can look a little bit clumsy, but don't worry, I'll make it as easy and simple as possible. I'll divide it into three parts. In the first part, we'll write the equation in terms of Laplace transform. In the second part, we'll insert the given conditions, that is, when x is equals to 0 and when x is equals to infinity. And finally, in the last part, we'll rearrange the equation algebraically. That said, let's get into it. Like I promised, we'll be looking at the Laplace transform of a differential equation and be using the first order. Now remember that if you have your y to be equals to f of x, if I'm to differentiate this, I'll get my dy dx to be equals to f prime of x. So today, what we're basically looking at is the Laplace transform of f prime of x. We're deriving the Laplace transform of f prime of x. Like I promised, we'll divide it into three parts. We'll write the equation in terms of Laplace first. So let's get ahead writing in terms of Laplace. Let's remember that the Laplace transform of any function of x. Let's remember that the Laplace transform of a function of x is written as e is between infinity and 0, e raised to power sx f of x, this is minus, with respect to dx. Now, for the Laplace transform of, sorry, there's, for the Laplace transform of f prime of x, I can easily rewrite it this way. This is the same thing as the integral between 0 and infinity, e raised to power minus sx f prime of x with respect to dx. Now, in solving this equation, the easiest way to solve this equation is to use our integration by parts. Integration by parts says that if I have the integral of u dv, this is the same thing as uv minus the integral of v du. So the first thing I want to do here is to pick my u and to pick my v. I can pick my u to be the same thing as e raised to power minus xx, while my dv will be the same thing as f prime of x. And if my u is equals to e raised to power minus xx, then I'll be looking for du. My du obviously will be the same thing as minus x e raised to power minus xx. While I'll now look for my v from dv will be the same thing as the integral of a differential will definitely reduce the differential order. So this will reduce that differential order to f of x. Now let me mention something here. Now note that I have reduced the differential order from dv is equals to f prime of x to v is equals to f of x. In selecting your u and dv, don't make a mistake to select your u to be equals to f prime of x. If you select your u to be equals to f prime of x, see, this is what I'm saying. If I'd made a mistake to have selected my u to be equals to f prime of x, definitely I will now be looking for du, which will increase the order of this differential to f prime prime of x. The equation becomes more complicated. Rather, I'll pick my dv to be equals to f prime of x. By the time I'm looking for v is equals to f of x, the complexity of this equation is reduced. So don't make this mistake. Don't make this mistake. Now with this, you can now begin to impute our values for u and v in our equation so that the Laplace transform of f prime of x will now begin to look as u and v. I'll pick my u, that's e raised to power minus x x f of x, that's my v, minus the integral of v, that's f of x dot du. That will be into minus s e raised to power minus x x with respect to dx. You can obviously, if you look at this, looking a little bit clumsy, but it's not clumsy. Now this is minus here. Definitely this negative sign will multiply. This negative sign will become positive. Let me just manage and write it. Okay. Now obviously what I've done now, I've just rewritten my equation. Now, the next thing we want to do now is we want to insert the given conditions. That is, the conditions when x is equal to 0 and when x is equal to infinity. Now, look at it this way. My Laplace transform of f prime of x will definitely become, when x is equal to infinity, this becomes e raised to power minus x into infinity f of infinity minus, still on e raised to power x of infinity. I'll apply the 0 again. This is minus x of 0 into f of 0. Now let's close this. Now minus, I now apply it to the integral. It's the integral of this to 0. But if you look at this integral, my negative sign must multiply my negative sign here to become plus. Then I can move the s outside. Then I have e raised to power minus x f of x dx. That we have applied the signs. That we have applied the conditions. Now let's solve our equation out. L prime of x will be equals to, now e raised to power infinity. Anything raised to the power of infinity is definitely 0. So that means the whole of this becomes 0. Then 0 times f of infinity is definitely 0. So I have 0 here. Minus e raised to power of s into 0. 0 times x, that's 0. E raised to power 0 is 1. 1 times f prime of f of 0, that's f of 0 plus. Now, if you look at this is still my s into e raised to power minus x f of x between infinity and 0 with respect to the x. Now, if you followed my last lesson, in case you missed my last lesson, please do not hesitate to check the description below for a link to that lesson. This is the same thing as the whole of this part of the equation here is the same thing as writing the Laplace transform of f of x. So I'll just write this as L into f prime of x will be equals to minus f of 0 plus s l f of x, SLF of x. Now with this I can rearrange my equations. Now like the third condition will be rearranging my equation so that L f prime of x obviously will be the same thing as s l f of x. Now the negative sign can come forward minus f of 0 minus f of 0. With this, I hope you understand how it works. And if you have any question, please do not hesitate to use the comment section. Thank you for staying with us and have a nice time.